Good morning. I am Dr.G.Shyamala, Associate Professor, PG and Research Department of Mathematics, Sita Lakshmi Ramaswamy College, Trichy. Welcome you all. In this video, I am going to give a small introduction about compound random processes. Understanding of the scientific developments and engineering applications of mathematics are to know how this discipline can contribute to technology to scale new heights. Probabilistic model are realistic than deterministic model. Compound random distributions. Introduction. Key tool of probability theory, that is inclusion exclusion identity and remaining. Introduction. Basic sciences are the roots of applied sciences. Advances in mathematics would be imminent for exploring the universe. That is, it explores the universe by certain laws. Stochastic models deal with indeterminism in dynamic studies. Probability theory is a part of mathematics which is useful in discovering and investigating the regular features of random events. It is extremely important in both understanding and applying probability theory to be able to think probabilistically. Mathematical models developed through probability theory for improving inherent interest and applicability, also for their usefulness in strengthening the probabilistic knowledge and intuition. Inclusion and exclusion identity. For any n events, E1, E2, E3, etc. up to En, probability of E1 union E2 etc. union En is summation over I P of Ei minus summation P of Ei intersection Ej plus summation P of Ei intersection Ej intersection Ek plus etc. up to minus 1 the whole power n plus 1 P of E1 intersection E2 intersection etc. En. This identity is used to find the distribution of number of events that occur. Types of random or stochastic processes are Markov chain, counting process, that is Poisson process, in general, renewal process and queuing process. A model for optimally making decisions are known as a Markovian decision process. It is also applied in genetics and production processes. A type of stochastic process known as a counting process is used to analyze greedy algorithms, minimizing highway encounters, collecting coupons, and tracking virus infections, etc. Conditioning. Conditioning is one of the key tools of probability theory, and when it is properly used, that enables to solve problems easily. It is defined by, for any two events A and B, probability of A given B, which is equal to P of A intersection B by P of B, where P of B should be greater than 0. Similarly, P of B given A defined as, it must be P of A intersection B divided by P of A, where P of A greater than 0. Compound distributions. Compound distributions are the resultant of combining two distributions in a particular way. The distributions with the probability generating function of the form Gy of Gx of S are called clustered or compound distributions. Consider a random variable x whose distribution depends on a single parameter theta, which instead of being regarded as a fixed constant is also a random variable following a particular distribution. In this case, we say that the random variable x has a compound distribution or composed distribution. Compound binomial distribution. Let us suppose that x1, x2, etc. are independently and identically distributed Bernoulli variates with the probability of xi equal to 1 is pi and probability of xi equal to 0 is qi. I varies from 1 to n. For a fixed n, the random variable, namely x equal to x1 plus x2 up to xn, is a binomial variate with parameters n and p and probability function p of x equal to r, which is defined as NCR p power r q power n minus r. R varies from 0 to n, which gives the probability of r successes in n independent trials with the constant probability p of success for each trial. Now suppose that n, instead of being regarded as a fixed constant, is also a random variable following Poisson law with the parameter lambda, then probability of n equal to k, which is defined as e power minus lambda, lambda power k by k factorial, k varies from 0, 1, 2, etc. In such a case, x is said to have compound binomial distribution. The joint probability function of x and n is given by probability of x equal to r intersection n equal to k, which is equal to probability of n equal to k into probability of x equal to r given n equal to k, which is e power minus lambda, lambda power k by k factorial into kcr p power r q power n minus r. Since probability of x equal to r given n equal to k is probability of r successes in k trials where r less than or equal to k. For example, suppose that the probability of an insect laying n eggs is given by the Poisson distribution e power minus lambda, lambda power n by n factorial, and the probability of an egg developing is p. Assuming natural independence of x, the probability of a total k survivors given by the Poisson distribution with the parameter lambda p. Another example, if the probability of number of hits by lightning during any time interval t is p of lambda t, and if the probability of its hitting and damaging an individual is p, then assuming stochastic independence, the total time duration t is given by p of lambda tp. Compound Poisson distribution. Let x be a Poisson random variable with the parameter lambda, so that probability of x equal to r is given by e power minus lambda, lambda power r by r factorial. R varies from 0, 1, 2, etc., where lambda itself is a continuous random variable with generalized gamma density, which is defined as given above. Considering two-dimensional random vector, namely x comma lambda, in which one variable is discrete and the other is continuous, then the joint density of x and lambda is given by probability of x equal to r intersection lambda, where lambda varies from lambda 1 to lambda 1 plus h, where h greater than 0 and lambda greater than 0. Compound Poisson process. A stochastic process, namely collection x of t greater than or equal to 0, is said to be a compound Poisson process if it can be represented as x of t is equal to summation over I varies from 1 to n of t yi, where t greater than or equal to 0. Here, collection n of t greater than or equal to 0 is a Poisson process, and which is the way random variable yi are identically independently distributed, which is also independent of the process collection n of t greater than or equal to 0. Assume that there are y number of clusters where y is a random variable. Let xi I varies from 1, 2, 3 up to y denote the number of objects in the ith cluster and x1, x2 up to xy are independently and identically distributed random variables. Also assume xi, I varies from 1 to 3 up to y are independent of y. Define n is equal to x1 plus x2 up to xy. Then n denotes the total number of objects in all the clusters. Feller called this process as generalization. Douglas called these distributions as stopped sum distributions because the summation of fx observation is stopped by the value of fy observation, where fy is the distribution of y and fx is the common distribution of xi. Let gy be the generating function of y and gx be a generating function of x. Then the probability generating function of the distribution of n is given by e of s power n, which is ey of s power n given y. That is ey of gx of s, which is gy of gx of s. The distributions with the probability generating function of the form gy of gx of s are called clustered or compound distributions. Common terminology is n has randomly fy stopped sum fx distributions. If y follows a Poisson distribution, then the distribution of n is called compound Poisson distribution. Palya-Apili distribution is a compound Poisson distribution with the geometric distribution as a secondary distribution. Minkova in year 2004 defined a compound Poisson process with the geometric compounding distribution and discussed some of its possible applications in risk models and ring probability. The corresponding counting process is called Palya-Apili process. Some existing Poisson stopped sum distributions are Niemann type A distribution introduced by Niemann in 1930, that is Poisson of lambda versus Poisson of phi by Gabe Mosel and Inal in 2013, and Hermite distribution introduced by Kemp and Kemp in 1965, that is binomial of 2, p versus Poisson of theta. The third one is Poisson-Pascal distribution introduced by Kellum in the year 1952, that is negative binomial of k, p versus Poisson of phi. One more compound distribution, namely Thomas distribution, that is shifted Poisson of lambda versus Poisson of phi. Compound distribution, Poisson distributions is introduced in the year 1962 by Conway and Maxwell as a two-parameter extension of Poisson distribution in queuing systems. It is generalization of Poisson, Bernoulli and geometric distributions. In the year 2005, Galit-Shimoli used this distribution for fitting discrete data. This distribution is flexible for fitting over and under dispersed data. Its probability mass function is probability of x equal to x is mu power x by x factorial power nu into 1 by z of mu comma nu. X varies from 0, 1, 2, etc. where z of mu comma nu is defined as summation over j mu power j by j factorial power nu for mu greater than 0 and nu greater than or equal to 0. Priyadarshini and Dr. Savitri in 2018 introduced compound Poisson distributions by compounding Poisson distributions and geometric distribution, namely Poisson Palya-Apili distribution, whose probability generating function is g of s is equal to z of mu s comma nu by z of mu comma nu. Traffic accidents and fatalities model, shock model, natural disaster model, and game models are framed using compound Poisson distributions. New problems in various branches of engineering and science do not fit into the framework of the classical probability theory. Such problem arouses us to study the processes, that is, phenomena that take place in time. Many problems that arise in physics, chemistry, and other fields can be solved by using random processes. Thank you.